Hello, everyone. Warm welcome. Good morning to people who are attending from ASEAN time zone, and greetings of the day for the people who are attending from outside Singapore. Welcome to AI Accelerate APAC 2021 online conference. Extremely happy to be presenting the first topic for this conference this year. And I'm Muni Vinay. I'm head of data and AI for Lazada. And today I'm going to talk about, the quantum computing and how the quantum computing is going to impact the AI hardware. And this topic is slightly going to be technical. I'm going to cover these technical topics as layman as possible, but just in case, if you could not able to understand, probably we all can share the slides, and then I've also prepared a ready reckoner for you. And of course, you can do your online research and then gain more understanding of the topic, because the quantum computing itself is niche, and some of the concepts that I'm going to talk in today is slightly technical. So with that, let me move forward, right? And let me help you walk you through how the agenda, or rather your knowledge path, is going to look like, right? So you're going to understand first the ML lifecycle, and then how hardware plays a vital role in the ML lifecycle. And then some of the key challenges with today's AI ML implementation, right? So then, because of that, you might need a quantum computing. And then why do we need a quantum computing? And then even before that, what is a quantum computing? And then eventually going to talk about how the quantum computer works. And then, of course, the building blocks of the present concept of the quantum computing. And then once we have these two topics, how do you combine together and then unlock potential value with a quantum AI? So basically, you're combining the quantum technology at one side and then artificial intelligence, and then apply. And then how do you unlock value, right? And then what is the current state? And then how the future state is going to look like for the quantum AI. And then, of course, key takeaways in the end. And then I also prepared, as I said, a ready reckoner in the end. So probably when AI Accelerate Institute share the slides, so you can also use that as a ready reference going forward. Okay, let's get started. How many of you know machine learning, right, or probably artificial intelligence? How many of you have been using machine learning, even if you're experimenting, probably maybe learning, doing online courses, and then trying to understand? Probably you can just leave your comments. But I'm sure most of us are getting into this area, right? Or rather, for most of the organizations today, this topic is one of the driving topics, right? It's in the driver's seat, especially with the COVID. I'm sure most of the automation and then most of the digitalization happening. So this is even more important for most of the organizations. But very high level, I'm going to touch base what it is actually required to implement an end-to-end machine learning solution. Obviously, most of you might be here. So you guys might be working on Jupyter notebooks. Basically experimenting, trying to learn stuff. So that's quite natural. This is where you usually start. And then eventually, this is not the machine learning implementation, right? In a real production world, the notebooks and Jupyter experiments is not going to get you the results that you needed. So basically, you need to look at automation in moving this to the production, and then using a version control and then storage using something like a GitHub. Is another level, right? So that is important too. So how do you operationalize this? At the same time, how do you automate the development? And then most importantly, obviously, you need to have a proper data set management, labeling, and then some control over the labeling. And then basically, you need to train the models, basically combine the experiments together, and then understand which model is working well. And then you need to obviously version the model. And then you need to deploy the right model and then serve them real time in the production. And then as we talk about the modeling, so it is also important to understand the compute power. So these two are interrelated, right? So basically, you want to train a heavy data model, or basically with large number of labels, and then or even you selected a use case where you need a different type of computing power. So this goes hand in hand with your model training. So I'll speak about it in a detail in the next slide. So basically, if you look at it, all these work together. And then, so you need to use together to have a meaningful or a powerful machine learning implementation. So, which is why it is, remember what I said, if you talk about machine learning, right, hardware is very critical. So, services, training, platform interfaces are all okay, meaning you need to have a knowledge and then probably some kind of infrastructure to do it. But I think one of the key layer of your AI ML implementation is hardware part of it. But the critical thing out of all is basically the memory and the logic. So the powerful AI models are trained usually well if you have a better memory, which means better random access memory and then better processing power. And then, so usually, if you look at the AI end-to-end AI ops, right? AI ML ops or AI ops, there are various names to that. So basically, there are 5 steps. Right? So you train your model, package your model, so you validate, deploy, and monitor the model. So then, if you look at me, the critical computing power or a hardware impact would come during training the model. So basically, as I said, so the larger the data sets that you have, the larger the data table or a labeled data that you might have, right? So then it requires more computing power to train a model. Imagine if you have 100 rows, these 100 rows with like, let's say 5 fields, which means in a metrics, basically we're talking about 500, 1 into 500 tensor. So then similarly, it exponentially grows if you have like 100,000 or a million. So basically, if you convert all these into a tensors, so then calculating on top of that, as I explained before, requires the computing power. And then the recent advancement being GPUs, everyone knows. So GPUs are powerful and a faster way, slightly faster way to train a model. And then these days, we also have tensor processing units, which is released by Google. So it's very helpful and then faster to perform a tensor calculation that I just talked about. And then also distributed learning. Instead of training in one machine, can I distribute my entire machine learning model and then train it like parallel, maybe 10 GPUs or 5 GPUs together. So that's been the trend here. So, but that's not the key challenge, right? So what's the key challenge, or rather, what are different limitations with the current compute? If you look at it, the basic fundamental element of a computer is a transistor. So basically, the larger the number of transistors work together, the better the computing power, the better the random access memory and storage, and then better it could able to calculate the classical computer can. So, but soon it's hitting the limit. The Intel is already working on 14 nanometer chips, and then if it is that itself, we're talking about, I think 8 times smaller than HIV, diameter of the HIV virus, and I think 500 times smaller than the red blood cells, right? So here, when it approaches 2 nanometer, that means that's the size of an atom. And then what happens? So if you want to build a transistor which is lesser than 2 nanometers, right, it will lose its the current physical properties. So beyond 2 nanometers, right, it starts behaving like a quantum. It starts adapting to the quantum mechanics. Explain that a bit what that is, right? So basically, what I mean to say here is the Moore's law, which is a guiding principle for scaling up a physical computers, is flattening it out already. So we need a computer that interacts and then calculates, operates at a subatomic level. So based on a subatomic particles. And second, encryption, right? The factor-based encryption that we currently use, which we currently use in the current markets, right? So it's been theoretically proven that if you have a powerful computer, it can easily be broken. So basically, these factors can be deduced by something like a Shor's algorithm. And then you'll be able to break the encryption. So the computers are not secure anymore. So AI models that you deploy and then that you encrypt and then the deploy, right? So it might not be secure anymore. So it can be tampered tomorrow. So basically your data that are used, the labels that are used, or even the AI model in the production can be tampered. It's quite possible. So we need to look at these advanced encryption methods to safeguard these AI models or from an encryption point of view. Last but not the least, let's say if you want to use AI for a drug discovery to understand the protein structures, right? So basically, these are biological and natural elements that we're talking about. So even though if you write a best AI model, because you've not considered all the scenarios, all the factors associated while modeling these naturally prone models, right? So it's not accurate. So you lose your accuracy, and then it'll be very inaccurate. Right? So here, I think the scientists are looking at and use nature, to model the nature basically. So you need something at a subatomic level again. use a combination of them to model something like a protein or chemical molecules. So here, most of these limitations, right, can be addressed something called quantum computer. I would recommend to start doing the research, because this is something that's going to fundamentally revolutionize what's going to happen in next few decades. I'll explain what the quantum computer and all in few slides. So let's understand what that is. So what do you mean by quantum computer? How is it different to a classical computer? Okay, let me ask you this question. It's a very simple question. How many of you know the prime factors of 17 or 1 and 17? Very easy. So basically, if you have a calculator in the hand, and then it's easy to calculate the prime factors of 2 digits. And I slightly increase it a bit, right? So prime factors of 91 are like 1, 91, 7, and 13, right? It's 4 factors. So far, so good. So your calculator, probably your physical computer can easily calculate. Think about this. A 232-digit prime factor. And then you might ask why you need this. So are we even looking at 232-digit numbers prime factors? Do we need that? Yes, so we do. In fact, scientists, when they're dealing with the drug discovery, as just pointed out, right, they need to look at so many scenarios, so many factors to understand the molecule structure then. Correct? And then, because of the limitation of the physical computer, right, it takes about 2 years to find, and then you need a sizable amount of money to even perform these calculations. So it's impossible to do it in an hour or a day using a physical computer. And then on the other hand, so why? Because if you look at it, the time in a classical computer, right, the exponentially increases, or basically when you're talking about breaking a large number of factors, so it's exponentially increases as the integer increases. Now take a look at it. A quantum computer, on the other hand, is a sophisticated approach to make the parallel calculation based on the laws of quantum mechanics. So basically use the subatomic particles and then use them to design a computer. And then it has been theoretically told that the 232-digit, the prime factor calculation, which takes about 2 years for a physical computer, it's theoretically being told that a quantum computer can do it within the hours. What? Seriously? At one hand, we're talking about 2 years. At one hand, we're talking about hours. How is that even possible? So just going from a atomic level to a subatomic level, how could this even be possible? Which is what I'm going to explain in the next slide. So this is where I think I'll be getting into many concepts. Keep a close eye. Keep both of your ears open, right? I mean, this is where we need to look at some of the. You need to understand some of the concepts to get the full grasp of what the quantum computer is. Again, let me ask you a question, right? So, how many of you know what this is? So 1000010. Do you know what this is? I'm sure people who understand the binary numbers, right, will be able to clearly tell what this is. Here I'm talking about A in a binary language, because the classical computers that we are using today understands or calculates, performs the calculations based on ones and zeros. So which is what a transistor will do, right? A transistor will turn on the switch, it's 1, and then turns off the switch, it's 0, and then it uses a combination of this through the gates, and then you have the calculation. So our classical computer, which means a memory unit in a classical computer, either stores as 0 or it stores as 1, correct? So meaning at any given point of time, it'll have 2 memory units at once. A transistor will have 2 memory units, which is 0 and 1. So meaning if I have 40 transistors, so I have 80 memory units. Basically, it's 2 times the n. So if I have, let's slightly understand what happens in a quantum computer. So it works in a concept called qubits. I'll explain what the qubits are a little later. So, but it can have a multiple states, meaning it can be both 0 or 1 at the same time, or in between. So it's like 0.5, 0.4, 0.3. So it can be anything at the same time, right? So, and then because of this, it's not just zeros and ones we're talking about here. So here we're talking about storing many memory units. What is a qubit? This is where I'm getting into the quantum concepts, right? For that, to explain what the qubit is, I'll explain this through an example of penny, right? How many of you know what this is? So this is US dollar, and then one is head and then one is tail. I can easily compare this with your transistor. So meaning a head can be a 0, correct? And probably a tail can be 1. So a coin, in this case, here it can be a 0 or it can be 1. So it has got 2 memory units. So this is same as your classical computers here, correct? So whereas, what about this? Can you tell if the coin is head or tail? It's basically spinning, meaning it can be both. It can be either head or it can be either tail. So 0 or 1. It can be anything. So meaning, or it can be in between. So this is what we call it a superposition. So meaning I will translate this into a quantum computer. Let's say if you put an atom or electron rather into a spinning mode, right? So basically that's superposition. So it'll have multiple states. So this is what we call it as a qubit. So then, so because it's a qubit, right? Ideally what happens? So you can use a combination of qubits and then you can entangle them. So meaning if I start a spin with the one qubit, I can make it in such a way that the other qubit also spins in the same direction. So with one qubit, I can predict and correlate the behavior of another qubit. So which is what we call as entanglement, a quantum entanglement. So if you entangle 2 qubits, right? Imagine this will have many memory points and this will have many memory points, right? So combined with these two, right? So basically it'll have 2 to the power of n times of memory that it can store. To help you understand in a simple layman terms, so if I have a 20 qubits, right? So I can store a million values in parallel. So whereas in a physical computer or a classical computer, it's just 40 memory units. So here I can have million memory units together. So why? Because of the 2 to the power of 20 is what we're talking about here. If I have a 50 qubits, this is interesting, guys, look at it. I can have a computing power, which is equivalent to the China's supercomputer, right? Which is Sunway Taihu, which works at approximately 100 petaflops. And then if I have a 300 qubits, basically that's a larger number, that's larger than number of the atoms in the observable universe. Here we're talking about 2 to the power of 300. So what's happening here is we could able to expand the computing power in an exponential way as we increase more qubits, correct? So here, right, after certain qubits, the quantum computer can perform calculations that a classical computer will never be able to perform. So not even lifetime, right? So it takes more than a lifetime to even perform. So which is what we call it, everyone calls it quantum supremacy. So at the point where a quantum computer could able to outperform a classical computer. So which is what is Google has recently, or rather a few years back, has achieved. Sycamore, that's its quantum computer. So recently China also has even done this, right? So what is this? So how is it even possible? So for example, can we build qubits? So meaning, can we just keep on adding the qubits and then build a powerful computer? May not be, which is what I'll explain in the next slide, right? So before I explain what the quantum computer is made of, I think the graph on the left could able to give you a understanding of what do I mean by that quantum supremacy. Basically here, right? So there is a threshold for a physical computer to work. So practical limits of a classical device is directly proportionate to the line of classical devices are basically the number of transistors that it can perform, right? So this is where you have atomic level and then maybe smallest nanometer that you can think of, beyond which, right, you would need a quantum computer to perform. So basically here, right, so here we're talking about 2 into n. So but here beyond this, right, so it's basically 2 to the power of n adds more computing power. I could able to cross the 2 into n computing power, and then it's better than your classical computer, so which is your region of quantum supremacy. So this is only an illustrative, right? We don't have a full-fledged, I would say, working quantum computer. So we have quantum simulators and then quantum accelerators now. So to build a quantum computer, a quantum desktop computer or a computer that you can freely use as a device would take about 15 years. So until then, it's conceptual, right? So basically, we're talking about quantum chips that could able to build the qubits and then calculates based on the qubits. and then you measure the outcome based on quantum gates and the measurement interface, obviously. So you perform the calculations using the quantum gates. So here you can entangle the qubits, add more qubits into the entanglement, and then perform the necessary calculations. And here you can measure, and then pass the feedback into the classical computer, and then take a decision or probably derive something that you're looking for. So that's how a quantum architecture looks like. And then this is again very, very theoretical and then technical as well. So there are various ways to build the qubits, so which is fundamentally going to increase your computing power. Right? So someone like IBM and Google uses something called semi-conducting loops. So what they would do is they would cool a material to minus 270 degrees, right? So which is Kelvin degrees. So which is where I think the material will have a superconducting nature. So here you can basically making sure because of the superconducting nature, right? So you can create that spin for the electrons. So you can put them into a superposition, correct? And then you can use something like a microwaves between two spins to create the entanglement. So different type of companies are adopting different ways to achieve this qubits that I just mentioned. But objective is one and the same, to build a subatomic computer, which is called quantum computer, which is more powerful than a classical computer. Okay, so I know these are so many concepts. It's for new guys, it's very hard to digest, but I think you can take these slides and then, as I said, you can do your own research to see what this is in a more leisure way. So at one hand, I talked about AI, and then the other hand, we talked about quantum computing. Let's understand how do we combine both. So if you look at it here, right? So ideally, what happens? What happens in a deep learning or a neural network, right? We are passing the data, right, into different layers, and then we're teaching them. We're splitting the data into the pixels, and then passing these pixels into the different layers. And then based on the composition of the pixels, you're teaching them what points are important and then what points are not important. And then based on the important points, right, you understand that an output is something. For example, it could be a dog here, right? So dog image is broken down into the pixel, and then you pass into the various layers and then see which ones are important, which one you can forget, and then filter down the information into the last level, right? And then with the high probability, you say either it's a dog or it's not a dog. It could be the same for, say, for example, a fraud detection model. So I have a labeled fraud data. I pass it through my neural network through different layers, and then in the end, I could able to say if it is I could able to train a data that and able to understand if it is a fraudulent transaction or if it is not a fraudulent transaction. Concept is the same, but as I said, right? Imagine we're talking about a big data. So we have 1 million data points here. So even to search these million data points, right? You need a big data architecture to perform the search. Then you need something like a graph-based machine learning models to even perform the necessary calculations here. So which is where I think there is a different way to do it. So how about converting the data into like a qubits, use a qubits to prepare a quantum data sets, and then use a quantum gates to evaluate the models, right? And calculate the samples or averages. So then pass those averages into the classical model or a hybrid model in this case. And then you evaluate the output, right? So this is a quantum way of working. So here the millions of the data sets, right? So it runs and deduces and gets trained or gets synthesized parallelly, and then all the averages are passed as an input to one of the layers, right? So basically, you can cut down all these unnecessary layers, and maybe you can only use 1 or 2 layers. So it's in an AI model, it's called pruning, right? So you can use smaller number of layers. So instead of passing the full pixels here, we're talking about averages, right? So which means that itself will reduce the size of a model. And then because it's a quantum computer, it could able to do the parallel calculations, the training that it is required to perform this, right? It's going to go down drastically. So I think Google has recently launched the framework for tensor, the quantum tensors. So basically using the quantum computing and tensors to calculate these models faster. So there are cases where this model takes about a week to calculate with a higher data sets of about 25 million parameters, or even if you talk about GPT-3, those kind of an NLP models, right, which requires about more than 3 weeks or 3.5 weeks to train a very large model, which has got trillion parameters, can be deduced into like, for example, 1 trillion parameters, which take 3 weeks, can be done in like within days. or even less than a day using this quantum way of computing. So where it can be used, usually anything regarding learning or simulation, game theories, quantum search, decision making, it's very, very powerful. So you can use quantum computing or a quantum AI to do it. So current state, there's been so much hype, right? So as I was just talking about, can we just keep on adding the qubits? Why don't we just build a 200 qubit or a 300 qubit model and then replace all the classical computers that we might have? That's not possible, because even though theoretically it's possible, right? In a practical way, these qubits, the entanglement between these qubits are extremely sensitive. Even a slight change in the atmospheric pressure, slight change in the temperature, right? You break the entanglement. So then, meaning the output that you're gonna read have a lot of noise. So it requires error correction. And then the output observance itself, right? It's not possible. It's all probability driven. So you pass a probability as an input and you get a probability as an output. So whereas classical computer, right, you get a defined output. So either a 0 or 1. It could be like it's a probability. So then decoherence. So all these are challenges with the quantum computer. And then imagine if you're using a superconducting the qubits, right? You cannot do it in the room temperature. You need to cool it down to a Kelvin scale, right? For a common man like us, it's impossible. So this is how, right? I think most of the innovation is happening towards that side. How do we deal with all these noise, decoherence, errors, all these, right? And then at the same time, the cost is pretty heavy. Most of the patents and investments are going towards this, right? How do I reduce this? So which is why can you really use a quantum computer and then take a decisions? Right? You can still use it, meaning it's available as a service, right? For example, if you go to the IBM cloud or even Amazon, you have something called Bracket. In IBM cloud, you have IBM quantum computing. You can experiment and see the power of quantum computer there. So, but largely these are all simulators, right? Which are offering as a cloud computing service. So basically, you can see, experiment, and see how this is helpful in your environment. And so can you calculate or can you solve some of the business problem using these experiments, or can you even come close? And then Quantum Brilliance, which is another Australian-based company, right? They're working on something called quantum accelerators. To your PC, you can just attach it as an accelerator, which still requires your cooling power and sometimes a computing power or electricity power that is required. But you could able to get not 100% of quantum computing capabilities, but maybe 10% or 20% of that. So it's still not there yet, right? So the ecosystem itself is evolving. The different type of the qubits that are constructed, right? Regardless of if it is an ion trap or superconducting, as I said, the noise is too much. And then pretty much remember the other problem to solve is how do you connect that quantum computer to a classical computer and then convert and present you the data. You need some kind of a compilers, a programming language, a standardized universal programming language to do that. And then imagine you need to integrate it to your neural nets and then converting your your physical data into a quantum data, quantum sampling, right? You need some kind of a frameworks and software to deal with it. As I said, we are still here, right? We just achieved the quantum supremacy, but to have a useful computing power, right, or a stable quantum computer, we are talking about at least a bare minimum 2030 or beyond that. So 10 power 6 is where actually we could able to really use it for a complex science or a complex implementations, right? To structure to model a chemical, as I said, drug discovery, etc. So which is at least 10 to 15 years away. So, but otherwise, yeah, the key milestones for quantum AI is we want it to be less error prone, and then we need to develop more open source frameworks for training, converting those normal data into the quantum data, and then converting the quantum, the normal neural network language into a quantum neural network language. You need open source frameworks, and then you need to bring in engineers to work along and then do that. This is easy. The second point is actually because we have the simulators, the world is already working on this. So probably by 2025, you have a better frameworks ready even before the hardware, right, to get into the space. And then we also need to develop a bunch of apps that can outperform the classical computers and all that. So these are some of the important milestones for the quantum AI. So to summarize, is it going to immediately impact AI hardware or AI infrastructure? As I said, at least from a cloud perspective, this is what is trending now, right? People are using these cloud services, and some companies, some investment banks like your Goldman Sachs, JP Morgans and all, they're using a physical quantum computer, right, which is your D-Wave installing in their premises, or even some of the cloud services offered by these D-Wave kind of a company, right? And then trying to use it in their tradings and then investment banking and so on and so forth. So as a CTO or CIO, CTO, or enterprise tech head, how do you deal with this? So how do you need to consider and then get into the AI? I would say, to summarize, right, may not be. So invest very slow, take it very slow. But by then, think about how quantum computing can fit into your technology investments, right? So are you the company that needs emerging technologies to stay relevant in the market? So that's fundamental, right? So you need to understand your business dynamics. So do you really need emerging technologies? If I'm a investment bank, money is everything. Right? So basically, then what I would do, I would need as advanced systems as possible to predict the stock markets and then take better decisions on investments. That's critical, maybe. So maybe I'll just experiment, which is what is happening with someone like Goldman Sachs. And second, you can still see quantum computing as an advantage. So meaning, can you design innovative products, or can you even bring faster to the market with these quantum simulations or quantum accelerators? You need to think that too. And then if these two are good, so then you need to come up with a bunch of use cases, right? You need to understand where you can apply the quantum computing, and then come up with the use cases that are quite relevant. Come up with, like, I want to try an experiment for these and see how it works, right? So that's how you're going to start your quantum computing journey. And then, as I said, instead of implementing a coolant that can cool down the chips, build the qubits, and then use microwaves and lasers to entangle the qubits, that requires lots and lots of investment. You can try something like quantum cloud services, as I said, which is readily available. So IBM, AWS, Google, Alibaba, all these guys offer as a service, right? So you can get that and experiment and see how it is relevant. And then you need to collaborate well with your the market vendors and also consultants sometimes, right? So there are some niche consultants who are already offering the quantum computing solutions into the market. And speaking to both of them are critical. With that, right, you also need to nail down a critical resource, meaning you need to identify someone who could be able to evangelize to the leadership and translate the quantum technology into the opportunity for your business, right? So we need someone like them. And then see how it can unlocks your business value. And then most importantly, it requires patience. As I said, immediately you'll not be able to see any results. It will take about 5 to 10 years to unlock results, right? So that's why you need to underinvest, adopt iteratively. That's important. I repeat, underinvest, but still have a look and try all these cloud services, then get the use cases and all. But by then, iteratively, as there is a progress in the quantum computing, see how it can align with your business. And then understand the hype versus reality for new technologies, right? This is important. Otherwise, it'll lead into the disillusionment, right? So you need to set the expectations to your management, right? So these are the key 8 points as an enterprise that you can look at before investing into the quantum hardware or before even getting into the quantum AI. So with that, I quickly wrap it up, right? So machine learning, we all see what the machine learning is, how the end-to-end implementation looks like, and then how hardware plays a crucial role, and then challenges with it, right? Most importantly, and then how these challenges can be mitigated in the future using the quantum computers. So basically interacting at a subatomic level and then calculate faster using qubits. And then we also understood quantum computer, right? The basic fundamental quantum computer works on qubits. And then there are various ways to build a qubit. And then if you entangle the qubits, you could be able to achieve the quantum supremacy that is required to outperform a classical computer. And then we can also unlock a value by combining the AI and quantum. As I said, you could be able to run the models faster. So you could be able to deduce the data that is in there, used for the training in a much more efficient way. Then the accuracy is better because we are using nature to model the nature. And but keep in mind, we looked at it. There are a lot of challenges with the quantum computers, a lot of noise, a lot of decoherence. Most of the investments and innovations are going on that side. A good quantum computer, a workable quantum computer is at least 10 to 15 years away. And then till that time, leaders, what they can do, they can gain necessary knowledge and then start slow, have an iterative approach to the quantum computing, use the quantum cloud services and experiment what is right for your environment, and at the same time set the right expectations to everyone. So with that note, I think I'm done, at least for the topic. As I said, I prepared this ready recorder, which you can carry. If you get the slides from AI Accelerate, you can keep these one-pager handy, right? So you can take a screenshot and keep it in your phone. And then if you want to understand more, so basically you can get into each of these topics and then deep dive research and then understand how it is relevant to your organization. Thanks a lot. Thanks for the opportunity. With this note, I would take leave. And then if you have any questions, happy to address that. Thank you. Bye-bye.